Hi, I'm Seth Stein, and I'd like to tell you what our research group in global seismology and tectonics at Northwestern University does. We do research. This is us presenting at the NAGU meeting. We do a lot of education and teaching, both in classwork and otherwise. This is us on the San Andreas Fault field trip. We do a lot of community activities. This is us at a meeting we hosted about the evolution of the Mid-Continent Rift and studies of it as part of the EarthScope program here on campus. And we do a lot of outreach here. We're filming a video about the Mid-Continent Rift and Lake Superior evolution, which is on YouTube. We have people with a wide range of interests and skills involved. The current cast of characters is 4 grad students: Reselling, Jamie Neely, Molly Gallahue, and Boris Rosler. Leah Soldich recently graduated, and our work today is still extends work done by Eddie Brooks before he got his PhD, and Miguel Marino. With 2 recent undergraduates who graduated, Maddie Lucas and Andy Gomez. Our primary collaborators are Carol Stein from UIC, Bruce Spencer from the Northwestern Statistics, and also Institute for Policy Research, 2 very distinguished seismologists, Sue Hoff and Norm Abramson, from the USGS and Berkeley, and our geophysics colleagues here at Northwestern, Donna Jurdy, Emil O'Connell, Chris Cotis. We also have a lot of collaborators from various institutions that we've worked with at different times relative to our current projects, and there are more than actually on the list here. And this network of collaborators is incredibly valuable and gives us a lot of expertise that we couldn't generate internally. Our goals are to understand earthquakes: how, where, when, and how they happen, and the shaking they produce. We're interested in the practical applications of this, using this to help communities better deal with earthquake hazards. We're interested in understanding physical processes of plate tectonics, how plate boundaries and plate interiors operate, how they've evolved. Our primary mission, in some sense, is to help graduate and undergraduate students start successful scientific careers in academia, government, or the private sector. We contribute to geoscience education through textbooks, articles about teaching and teaching methods. Our courses are typically available on the web. We do blogs on education-related topics, and we do a lot of public understanding and outreach about geoscience via the print and electronic media, YouTube, worked with museums, National Park Service, and other groups. And then we are fairly active. We're active in the earth science community worldwide: the AGU, the SSA, GSA, and the EGU. Our guiding philosophy comes out of a book that I read the year that I was a postdoc, planning on what I would do when I came to Northwestern 42 years ago. And it was a wonderful book by Peter Medawar called Advice to a Young Scientist. And title sounds a little arrogant, but he did win the Nobel Prize in biology and went on to become a very distinguished biologist. He said in terms of aspirations, any scientist of any age who wants to make important discoveries have to study important problems. In other words, so we try to always look at problems that we think have major implications, or we hope will have major implications if we're successful in studying them. So we're aspirational in that regard. We follow Medawar in saying independence is really important. He said that the best advice he could give is, don't worry about conventional wisdom. The intensity of a conviction that a hypothesis is true has no bearing on whether it is true or not. And the importance of the strength of our conviction is only to provide an incentive to see if it's really true or not. When someone says everybody knows something, you want to decide, is that really true? Medawar makes a big pitch for openness, that if you shut your door, you keep out more than you let out. And he said his group was always to tell everybody everything you know. So we try to be very open internally in our discussions, and also to communicate externally everything that we're doing. And he said you have to have a strong obligation to the truth. And that's especially important for us when we deal with things that have policy and hazard implications. Perhaps most famously, when we first showed that, unlike what people had previously thought, that there's no observable ground deformation in the New Madrid zone. Controversial result, and we got it. It's since been confirmed repeatedly. But now, in terms of earthquake hazards, we're finding what appear to be problems with earthquake hazard mapping. We don't fully understand what's causing these problems, but we talk openly about what we're doing and what we're learning, and we share it as we go along. Our current research themes, and these are basically involve multiple people and they sort of overlap. So it's not like some people work on several of these things. We're developing a new model for earthquake recurrence and probabilities. We're assessing how well earthquake hazard maps work and how to improve them. We use big data, large collections of data and methods for analyzing it to study earthquakes. And we're investigating continental rifting and passive margin evolution. So let me give you a brief overview of each of those activities. Most of you know, ever since the 1906 earthquake, the dominant paradigm in seismology has been the earthquake cycle. Strain accumulates between large earthquakes when the sides of the fault move, but the fault is locked by friction and so won't slip. Eventually, the strain accumulated is more than the fault rocks can withstand, and the fault slips. And over time, this causes quasi-periodic earthquakes. And here's a classic simulation. In this case, I'm doing a low-end block slider model. The slider here is a dove bar, a soap bar that I'm pulling on with on a yoga mat. I'm pulling on it with a rubber band. And of course, eventually the strain accumulated in the rubber band is enough to overcome the friction, and we get this quasi-periodic slip. So if the world were to work that way, we'd have quasi-periodic earthquakes. And in each case, displacement would accumulate as a steady, accumulation of stepwise. And in each earthquake, the strain that accumulated would be completely released, so the fault would reset. And in that case, the time to the next big earthquake would depend only on the time since the last big earthquake. But the geologists have known for a long time that faults don't work that way. They see what they call supercycles. These are patterns of clusters and gaps that are longer than individual earthquake cycles. So you'll see that in the earthquake history. You'll see the cumulative displacement. You have periods when you have a lot of cumulative displacement, then you have periods where you have very little, and you go through these things. Or conversely, when they try to infer the strain, you'll see the same. Strain builds up, released in a group of earthquakes, builds up for a while, released in a group of earthquakes. So what these say is that the fault has long-term memory. Not all the strain is released, and so the fault is not reset. The time to the next big earthquake depends on the history of previous earthquakes. Now, these supercycles have been observed in lots of environments around the world, plate boundaries and plate interiors. And so we've developed a model which tries to describe this supercycle behavior and forecast its evolution. We call that model long-term fault memory. And the idea is that the probability of an earthquake is proportional to the accumulated strain. That strain grows steadily between earthquakes at some rate A, and it's released in earthquakes in a strain drop R. And so A controls the long-term rate at which strain accumulates, and R controls that released in the earthquakes. So if R is small relative to A, the probability can stay high for several earthquakes, giving us a cluster. And then once a lot of it's been released, then we'll have a long period of time where it builds up again. So the important thing in this scenario is that A and R control the sequence properties. When they occur is governed by the probabilities, so there's still the randomness in there. And the quake probability depends not just on the most recent earthquake, but on previous earthquakes. So it's kind of like sports things where you can think of the fault as having a hot streak, and those are the clusters, and then you have slumps where you have gaps. And just as you wouldn't want to predict the behavior of a sports team based only on their previous game, you'd want to use the rest of the season. Similarly, earthquake probability depends not just on the history of the most recent earthquake, but on the history of the past earthquakes. Jamie Neely has followed up on Leah Saldich's work on this, and basically he's done this to try to estimate the probabilities of earthquakes on the Mojave segment of the San Andreas Fault, where the last big earthquake was in 1857. And so we used the data from the Pallet Creek record, and Jamie has taken the Saldich et al. Model which is written as a difference equation, and converted that to a Markov chain. In other words, a set of discrete states. And from that, he can calculate the probability of transition from one state to the next. From that, you can do probability calculations. And applying this to the Mojave segment, you see the following. Your last big earthquake was in 1857. The orange is long-term fault memory, and the Purple is the abnormal model. This is the Browning passage model, which is the preferred USGS model. And you can see that right now what's happening is that if an earthquake does not happen soon, the probability of an earthquake will level off with time, or log normal would even decrease, which to our way seems non-physical because the fault, if the earthquake hasn't happened, the fault is continuing to accumulate strain on it. The long-term fault memory has that property. In other words, it will continue to rise. And so over time, if an earthquake doesn't happen, long-term fault memory will predict significantly growing and higher probabilities than Browning passage. The next thing is to look at the Pacific Northwest using this sort of thing. As you all know, there's a lot of interest in the possibility of a big earthquake there. There are a lot of very scary stories about in the news media. All kinds of probabilities are quoted with no idea where these numbers come from. Things are overdue. And it turns out that those numbers are not at all well constrained. Basically, the actual data here is the paleo earthquake history. And what that shows is, again, gaps and clusters, gaps, clusters, and over about 10,000 years. The last big earthquake was in 1700. So the question of what the probability of earthquake is in the calculations depends wildly on whether you assume that you're in the cluster or you just use all the data. If you're in the cluster, then by definition, it has a smaller mean time between earthquakes than as a whole, a tighter standard deviation. So if you assume you're in the cluster, you can get probabilities that are up to about 6 times greater than if you use all the data. And that's pretty much independent of the probability density function that you use. The big issue is, are you in the cluster or aren't you in the cluster? And Jamie Neely is now working on trying to build the earthquake history into the long-term fault memory model, and hopefully we'll have some neat results for us soon. Another big project we're engaged in is looking at earthquake hazard maps. Probabilistic seismic hazard maps try to predict future shaking. So this is the USGS map for California and surroundings. This is the probability of shaking with a 10% probability of exceedance in 50 years, which corresponds to a map with a 470-year return period. And to do this, you make assumptions about how large and how often future earthquakes will occur and what shaking they'll cause. The results go into building codes for earthquake-resistant construction. And the problem is that although this has been used for about 40 years, we really know essentially nothing about how well it actually forecasts the shaking that occurs. So what should it do? Well, at a point on the map, the probability that in T years of observation, so you'll exceed the value on a map with a big T year return period is this exponential. And since we don't have hundreds of years of data, you can convert this time to space, and the fraction of sites where the observed shaking exceeds the map value should behave the same way. So F here is the fraction of sites at which above this 45-degree line, these are sites where the observed shaking is greater than the predicted shaking. That number will start off very small at the beginning of a return period, and then with time, the number of sites that exceed the mapped value will grow. So by one return period, that would be either 475 or 2475 years, 63% of the sites should have values higher than are shown on the map. Now, the problem is that we don't have long periods of observation. So our data will be down around here, fairly close to when the map was made. But we can get around this by hindcasting. In other words, we collect data from the past and compare those data to the predictions of the hazard map. We've done this for California in something called CHIMP, the California Historical Intensity Mapping Project that Leah Saldich has led. Looked at all the earthquakes that we know that have caused significant ground motions in the past 160 years, and we plotted the maximum shaking at sites throughout California. So this map here shows the maximum shaking in intensity units at all the different sites where we have data. And then these are the USGS maps. Now, you would expect the following. We're about a third of the way into this return period. So we would expect about a third of the sites should be higher than is on that map. And in fact, far less than that of those sites, in order of magnitude less sites actually have exceedances that are that high. Same is also true if we use the 2475-year map. So the current USGS maps significantly overpredict the shaking in the CHIMP dataset. And we weren't all that surprised by this because previous works, this was Eddie Brooks's work, had shown that the same thing is true for Japan, the compilation of shaking data, and you compare that to the map, again, you'd expect about 66% of the sites should be above this map on 475-year map. 500 years of data is about the same as return period, and only about 27% of them are. So again, the map over predicts the shaking. We saw that just recently shown that this is also true in France. 66% of the sites should exceed the shaking shown in the map, and only about 34% do. So taken as a whole, the takeaway is that everywhere we've looked, the PSHA maps overpredict the historic shaking. And these are different areas with maps compiled by different people and data compiled by different people. So if the data sets are correct, then the map overpredicts shaking. On the other hand, if the maps are correct, then the data sets don't fully capture the shaking, or of course, some combination. And Molly Gallahue is tackling this for her thesis, and we hope to have some exciting results from that soon, from what Molly and Norm Abramson and Sue Hoff and everyone else together will have. So Molly will hopefully tell us some really neat stuff in the next year or so. Third big line of effort is what we call big data sets. And the idea is that traditionally seismologists studied individual earthquakes in detail, but it was really hard to tell if you could generalize the results from one study to lots of others. And you were combining studies that were done in lots of different ways and inconsistently. Now we have large global data sets and catalogs that can be analyzed consistently. And we can look to see whether we have geologically or statistically meaningful patterns. And one of the most interesting things we can do is when we have multiple studies, we can use the consistency to try to get a handle on the uncertainty. So here's a study by Boris Rosler. He's looked at 5,000 moment tensors that are both in the USGS and the Global CMT project. The differences between the moment tensors are typically an order of magnitude greater than the reported errors. So that suggests that the reported errors greatly underestimate the real uncertainty in fault parameters. Boris has also done an even bigger study involving almost 13,000 earthquakes from 7 different earthquake catalogs. And what he's looking at are the non-double couple components of earthquake solutions. These are the parts of the solution that are more complex than slip on a fault. And so the question is whether that's a real process or whether it's an artifact of a complicated seismic moment tensor inversion process used to get the moment tensors from the seismograms. It seems that no matter how you divide up the earthquakes, whether by magnitude or by fault type or by geologic environment, the average magnitude of the non-double couple components is about 20%. This consistency suggests to us that these are probably, a lot of these are not real. They're probably artifacts of the inversion. And Boris is going to be doing a bunch of numeric experiments to try to decide if that's really true or not. Jamie Neely has done a similar project looking at earthquake stress drops. Stress drop, the change in stress before and after an earthquake, is what controls the high frequency shaking that does the most damage to buildings. But it's an incredibly difficult entity to measure from seismograms. So you can do it in different ways, and none of them are very good. So Jamie has compared stress drops for 900 earthquakes that have been studied by 2 groups using methods that should be mathematically equivalent. And there's essentially zero correlation between the results of the 2 groups. The estimates for a given earthquake differ by orders of magnitude. So this implies that the uncertainty in the stress drops is very large, and that's orders of magnitude. And as a result, stress drop differences that are reported between earthquakes and, let's say, different tectonic environments may not be real because these differences are small compared to what appears to be the uncertainty in the stress drop. So, for example, it's been argued for a long time that earthquakes, intraplate earthquakes, may have higher stress drops than plate boundary earthquakes. Whether that's true or not is pretty hard to say given the uncertainties involved. I think it's quite possible that it's not true. Jamie has also looked at why continental normal fault earthquakes have smaller maximum magnitudes than thrust and strike slip events. And this is important for estimating hazards in places like Utah, East African Rift, or Italy, because a lot of the hazard comes from the very biggest earthquakes. And here's a p-value set data, and you can see that the largest normal fault earthquakes here in the purple never get above about 7.1, and that's a lot smaller than the largest strike slip or thrust fault earthquakes. Now, Jamie's simulations say that this is not an artifact of the short. It's about 120-year data set available. If bigger normal earthquakes occur, we'd have seen them. It's not a consequence of other factors, including the one that I thought would be the right answer, which was the length of normal faults available. My original thinking is there just weren't normal faults big enough to accommodate these things. Turns out there are. So it looks like the real variable here is lithospheric strength. The lithosphere is a lot stronger in compression than it is in extension. And so basically the idea is that you can't store up anywhere near as much energy for a big earthquake in an extensional region as you can in a compressive region. Jamie's also looked at the question of, have we seen the largest earthquakes in Eastern North America? Along the Canadian coast, we get magnitude 7s. Along the US coast, we tend to get 6s. And maybe a 7 at Charleston. So the question is, could we get bigger earthquakes than this, given how infrequent these are? Our catalog may not sample this very well. Jamie has generated a lot of synthetic catalogs and then sampled them over the few hundred years that we have data. And generally what happens is the maximum magnitudes that come out of these catalogs are a lot shorter than what really is out there. So we think it's likely that the largest future earthquakes will be significantly larger than those in the historical record. And it's also likely there isn't much real difference between the Canadian part of the margin and the US part of the margin, which was a little disappointing to me, since my theory had been that they were bigger in Canada, and that was because of the effects of the deglaciation, the ice removal. It may be that doesn't look like that's actually true. Last major theme we do is our tectonic studies. And right now our current focus is how continents rift and cause passive continental margins. Now our idea of conceptually, we know that the Wilson cycle describes this. The Wilson cycle explains that continents are stretched, they break up, young ocean forms, and that already has passive margins on the continents on either side left over from the breakup. The ocean grows, eventually it shrinks, it closes, and we have a continental collision, cycle starts again. But the cycle concept doesn't tell us why and how continents break up. So what we've been doing is we've been combining insights from present rifts, like the East African rift, from past failed rifts, like North America's mid-continent rift, in which we put a lot of effort. That's our sort of neighborhood big rift, and data from volcanic passive margins off the coast of Norway that Molly Gallagher has been looking at the data that's available for those. Try to put those together because they're on different stages of an evolutionary process. Presently extending rifts, like in Baikal and Kenya, can go one of two ways. They can either evolve into a seafloor spreading, and the structures will be left at passive margins on either side, or those rifts will fail, and those will give us things like the Real Foot Rift, where the New Madrid earthquakes happen, or the Mid-Continent Rift. So we spent a lot of time looking at the Mid-Continent Rift. There's lots and lots of data from studies that have been done before, and a lot of people now are studying it. It's the classic failed rift, and it's a major structural feature of the central US. The nice thing is it outcrops near Lake Superior, which produces a lot of beautiful scenery, but also lets you see what the rocks actually are. For the rest of its 3,000 kilometer length, it's buried, but because the rocks are dense and highly magnetized, they can be tracked on gravity and magnetic maps, as a gravity map. And it's impressive. They're about 2 million cubic kilometers, structures about 3,000 kilometers long, formed about 1.1 billion years ago. And the important thing is it preserves a record of how rifts evolved up to the initiation of seafloor spreading. It's a snapshot just before seafloor spreading started. We've been looking at this in a fair bit of detail, starting off with the seismic lines that have been conducted across Lake Superior that show us the rift basin, both the volcanics and the sediments in it. Our colleagues Jonas Clay and David Indell have done structural modeling of this phenomenon using balanced cross sections going backward in time. So we see that rifting starts, extension. We then have volcanism, deposition of volcanics in this basin, and activity on the faults along the side of it. Eventually the volcanism stops, but we continue to get subsidence, and hence sediments are deposited in the basin. Eventually the mid-continent rift was inverted, that is, compression squeezed it. That brought the igneous rocks up to the surface, where with erosion we can actually see them. We think this occurred when the mid-continent rift was the boundary of a large microplate. You might call it the Illinois microplate, and that's between the two big plates of Laurentia and Amazonia that were diverging. And if it's a microplate, we can do the kinematics of the microplate by using what we know about Microplate kinematics that we've done from our studies in the oceans, where we have a good handle on the kinematics of microplates because we have marine magnetic anomalies. Here, of course, at 1.1 billion years, the paleomagnetic data doesn't give us that much detail. So what are we doing now? Reselling is investigating the similarities and differences between the mid-continent rift. Its two arms are actually somewhat different. The southern Oklahoma Lockogen and the Reelfoot Rift. And as you can see from the gravity data, the mid-continent rift and the southern Oklahoma Lockogen have highs, and that's because they were inverted and igneous rocks were pushed closer to the surface. Reelfoot Rift appears to have not reached the inversion stage, and so it doesn't have much of a gravity anomaly. And so Reese is putting together a picture using lots of different data from all the sources out there, try to understand better how these things compare. We can also use the mid-continent rift to study rifted continental margins because they look like what the mid-continent would have evolved to had it split and started seafloor spreading. When we look at a rifted margin, we see a very characteristic set of features. There's a huge magnetic anomaly from the thick volcanic rocks there. That's much bigger than the seafloor spreading anomalies that are formed on the later formed oceanic crust. Volcanic units, we have seaward dipping reflectors that dip toward the ocean side. And then we have high velocity lower crustal units, which at least in part are the material residuum from which the seaward dipping volcanics were extracted. And we see those on the mid-continent rift. We've already seen the big, huge magnetic anomalies associated with the rift volcanics. And at depth, there is an underplate, which is, again, was from where the rift volcanics were extracted. So if the mid-continent rift actually started seafloor spreading, it would end up looking a lot like this. So we can get insight into rifting processes by studying the volumes of the onshore and offshore volcanics at passive margins, and in some cases, the associated large igneous province is like, for example, the Central Atlantic Magnetic Anomaly in Camp, compared to what we see along the coasts of on different sides of the Atlantic. Molly Gallagher has compiled the data set of the volumes of the seaward dipping reflectors and the volumes of the high velocity lower crustal units. And it turns out there's a very characteristic pattern. There's typically the SDRs are about a third the volume of the deeper high velocity lower crustal zone. And so it tells you that these things are formed the same way as part of the same process. In other words, that the SDRs are extracted from the HVLCs. And Carol Stein is now looking at how those compare to the volume of large igneous provinces. And from that, we are able to go back and we're revisiting the classic model for how rifts work. This is the model that John Dewey and Kevin Burke developed in the 70s. And their idea would be that there were hotspots. And at the time, they just meant these were domal uplifts with magnetism. Rift arms would extend out in 3 arms. Some of these would link up to form a new spreading center, and the continent would break up along that, leaving a new ocean basin. The failed arms that didn't part of that, and it's 2 out of every 3, are called the Lockogens, and they're left in the continent. From what we've learned now, we can see that what's actually happening is these rift arms are often boundaries of microplates, like mid-continent rift, and the microplate boundaries accommodate motion between the major plates. Eventually, when seafloor spreading is fully established, these other arms are left as fossil microplates, and we can see those on land. A lot of the magmatism is preserved, and we can see that at depth in the underplated layers or offshore. And more generally, many of the structures formed at the rift survive at the resulting passive margins. So a lot of the passive margin structures are inherited from the rift, and we can see them in the fossil rifts like the mid-continent rift. And it looks like hotspots are not all that important in the continental breakup. If you look at the volumes of magma up and down the ridge, and Molly has been doing this, they seem to be controlled much more like distance from the order pole. So this is a passive, mostly a passive response to the extension rather than an active process. The location of the hotspots seem to have much less effect on the volumes of passive margin volcanics. So in summary, this will give you an overview. Our basic takeaway from all of this is we've learned over the years that studying seismology and tectonics is challenging, it's interesting, and it's a lot of fun. Thank you.